All right, so I'm going to go over the answers to the free response questions in the assignment for this week on simple harmonic motion. And so let me bring up the assignment here, if I can find it. Okay, here we go. All right, so we have three different questions here. The first two are about pendulums, and then the last one is about a mass and a spring. And remember, when we're dealing with simple harmonic motion, those are really the two things that we look at, is masses on springs and pendulums like this. Those are the two big areas, I guess. And so feel free to stop the video, but I'm just going to kind of go through not so much I'll go through the numbers actually. And so what we have on this first one is we have a simple pendulum with a mass of 1.8 kilograms attached to a string of length 2.3 meters at an angle of 30 degrees. And then it's attached by this horizontal string right here to this wall. And then at a certain point, I think in part C and D, you cut that string and then you have to calculate some things. And so let me switch screens here. All right, so we have a pendulum that's hanging down like this. And it makes an angle with the vertical of 30 degrees. We have a mass of 1.8 and a length of the pendulum of 2.3 meters. So this length is going to correspond to 2.3 meters. And this mass is going to equal 1.8 kilograms. All right, so the first thing it wants is a force diagram. And so therefore a force diagram is going to, well, I'm going to draw a dot first to represent our bob, our mass. And so the force diagram is going to look like, well, there's some tension going this way, like this. There's also some tension, which I'm going to call TH for horizontal tension. We have some tension going that way. And then we have the weight of the bob, which is going straight down. So our force diagram is going to look like this. Two different tensions and one weight going straight down. The next part wants us to calculate this value right here of the horizontal tension. In order to do that, we need to resolve this tension into its component parts. So although this is what the force diagram looks like, I'm going to redraw this force in terms of its components, because then I can see a little bit easier how those forces add up and the fact that they're in equilibrium and stuff. So this is going to be our tension in the y direction, the vertical component of the tension. And this is going to be the tension in the horizontal direction. I'm going to call that Tx. Now, because it's an equilibrium, we can see that Ty is balanced by the weight, and we can see that Tx is balanced by this other horizontal tension. And so my two equations would be, well, for Ty, I'm going to write T cosine theta is equal to mass times gravity. It's these two vertical things. And then I'm going to write T sine theta is equal to the horizontal tension. Like that. All right, and we need to solve for TH. I say, okay, I just need to multiply my tension by sine theta. I don't know what my tension is though. But what I can say is that, or what I can do is I can solve for my tension here and then plug it into this, and then I'll be able to solve for my horizontal tension. And so I would do T is equal to mass times gravity over cosine theta, like that. And then I would say whatever I get for this value, I would plug into my tension right here and then solve for the horizontal component of the tension. And when I do that, let's see, let me look at the final answer here. When I do that, I get a value of about 10.2 newtons. And so TH is about equal to 10.2 newtons. Roughly 10.2. All right, the next part of the problem wants us to solve for the velocity at the lowest point. And so whenever I'm solving for velocity, I always think in terms of energy, at least that's where my mind goes initially. And so what is my energy? Well, at this point, before the bob is released, I have all potential energy. And at the lowest point, I have all kinetic energy. And then it goes back and forth, being converted back and forth. So at the lowest point, I can say that all of my kinetic energy is due to my initial energy that's in the form of potential. In other words, my potential energy, UG, is equal to the kinetic energy at the lowest point. And so my potential energy of gravity is just mass times gravity times height. And my kinetic energy is just 1/2 mass velocity squared. Okay, well, I see the masses cancel out. I can solve for velocity because I know the gravitational acceleration. I just need to know the height. And when we're dealing with pendulums, feel free to look up this derivation, but we're dealing with pendulums. We can say the height is equal to the length minus length cosine theta. It's a really common derivation if you want to look it up, but I'm just going to take it as a given. And so if I plug this back in, I'm left with, after I cancel the mass, I'm left with g times length minus length cosine theta is equal to 1/2 v squared. And so now I have everything I need. I have the angle theta of 30 degrees. I have the length of 2.3 meters. I have my gravitational acceleration of 9.8 or 10. And so when I solve for velocity, I get about 2.5 meters per second. 2.5 meters. So that's the velocity at the lowest point. And then the last part of the problem says, what is the, or how long does it take to reach that lowest point? And so we need some way to relate time to the pendulum's oscillation. And we can do that by saying that the period, remember the period means how long it takes to complete one cycle. So it's going up and then back. So we can say that that period is equal to 2 pi times the square root of length over gravity. Notice here again that the period does not depend on the amplitude. It does not depend on the mass. It only depends on the length. And so the length of the pendulum, we know, okay, but this is the time to complete one complete revolution. What we're really looking for is a quarter of that revolution. So therefore I'm going to divide this by 4 to get our time to reach that point. So that's just 2 pi divided by 4 times the square root of length over gravity. And you can see that this simplifies down to pi over 2 times the square root of length over gravity. And so that would be our answer there. And you can plug in the values. My final answer is about 0.76 seconds. All right, so in the next video, I'll go over the second problem.